once we have this, theory says that there is some plane which has, I don't know what to say, let me call it beta here and logarithm of z. Remember, for us, sometimes it's natural to use logarithm of z because that's a natural continuous variable. We have this thing that z or e to the s have good connections. But in this plane, if you plot a zeta function and you demand to find where is dynamical zeta function as a function of z and v. So this parameter has to do with finding things like escape rates and natural measure. You know, that's a dual parameter to time. This is time. That's dual parameter to it. And beta is your handle on computation. And we know that by probability conservation, 1 over zz, there's one eigenvalue where we don't weigh anything and we just look at Perron-Frobenius. And if we have probability conservation, and we have to, it's a compact space, then the leading eigenvalue has to be, eigenexponent has to be 0. So we know it goes through 0. We know that the first derivative of this thing, d beta of this function as evaluated 0, that has to do with expectation values of our observables. For example, in this case, expectation value of velocity. The second derivative is the one we're talking about here. Now, when you look at this formula, it's extremely easy to compute the second derivative because it's a product of terms. It's a product of all possible p's here. And as we look at all these terms, each one of them has extremely simple dependence on z and p. It depends on z as z to the total length of a pseudocycle, and it depends on beta as a dual to the total walk of a pseudocycle. I add up various distances in this. So that now, the fact that derivative, know how to compute derivative of these things with respect to beta, that's just beta I, it's a vector. That's just ith component of this guy times the rest, totally trivial calculation. And I know how to compute, for this polynomial, it's convenient to look at this object. It has to do with the relation to the logarithm. If I compute that quantity, what I'll get down is just the period, and then the rest will be the same. So the derivative with respect to our parameter dual to distance, so it's some kind of momentum in this case, it just gives me the how far I went in a space, and with respect to the dual variable to time, this guy, it just tells me how long it took. So it's extremely simple calculation. And we also have that Tp as a function of z beta. For these guys, z equals 1 and beta equals 0. This thing is 1. It's just 1 over the stability. So if z equals 1, I lose this dependence. If beta equals 0, I lose this dependence. So that's a special value, and that's where I'm computing my derivatives at. So it turns out these derivatives with respect to beta are just trivial to do, extremely simple. When you have them expressed in terms of periodic orbits. You know, they're profoundly mysterious when you look at the evolution operator, because it's some operator in infinite dimensional space. God knows what it means, right? But if you express them in sums of periodic orbits, they're extremely simple. And we get, in this particular case, we get a formula for diffusion, which is 1 over 2d, this guy here. And then, you know, it just looks totally natural. But you will never be able to find this in physical letters. To get to this formula required the whole course. So, yeah, I don't see any shortcut. If I knew a shortcut, I would have taught it. So it's a ratio of square of how far you got. But each one of these things is very easy. So, for example, the average of the time in this particular case will be, you know, I just get these things here. So it'll be sum over all pseudocycles. So that was the product. I'm sorry, I erased the zeta function, but that was the product of weights as you express it. But no weight, no prime cycle appearing more than once. So there's this thing here. And then you get -1, k plus 1. This is for the length of pseudocycle. And you get a product of stabilities in the pseudocycle. I mean, this is how many products you have, pk. And then you simply add the time it takes you to go around the pseudocycle. So np1. And if you decided to make a prediction for a real-time experiment, so, you know, for this bouncing experiment, what you do is you listen to your array, and every time you hear a click, a bounce, you say that's time. But you could actually put your clock and see how long it takes me to get someplace. Then these will be periods of prime orbits, the real ones in real time. That's very simple. So that's the denominator. So this looks okay. Dimensionally, it's fine, right? It's expectation value of distance squared divided by expectation value of time. It took me to do this. You know, it looks like a totally natural thing, except the formula itself is not so obvious because of this minus sign. And the other guy, this one, x squared 2, in a big space, how far I got. And now, you know, this little zeta means I used a Riemann zeta function, not Riemann, dynamical zeta function to compute this slope. But I could have also used the spectral determinant. So the formula will look the same, but it'll give me the, you know, it won't be so easy to write, but numerically it'll be actually a better formula than this formula. That's because it has better analytics, the properties, the curve that I'm plotting here. And this guy here is the same. It gets weighted by the pseudocycle. So this is the only thing that survived when we stopped counting and when we set beta equal to 0. So this is sort of geometrical size of the neighborhood of a periodic orbit, this thing, or a pseudo-periodic orbit. Then, because I'm looking at non-repeating pseudocycles, I have a sum, and then there is -1, k plus 1, the same thing. And now, you know, it's just beautiful. I just add up how far I got along a pseudocycle. So that means, you know, first I followed this guy, but then I follow the other one and the other one. So I'll have the right symbolic dynamics, but actually my trajectory moves a little bit because, you know, I'm using one thing to shadow a long orbit, and I'm using another one to shadow a long orbit. So I have a pseudo-orbit shadowed by a bunch of consecutive cycles. And this thing brings you someplace. And that's what it brings you. And then you square the distance, you average over all pseudocycles, and you get the diffusion constant. Now, this is an exact formula. We made no probabilistic assumptions of any kind. You know, there are no Gaussians, nothing. It's not noise. It's not Langevin, Einstein, and zillion other people. This is just the formula, and the only question is how good is the calculation. And that question has to do with understanding the convergence of this sum. You know, it's exponentially decreasing because all of these things are unstable, so longer and longer cycles are exponentially smaller. So it's going to converge and converge nicely, but it's exact. No hands. And just let dynamics do it. So what I'll do next is I will work through one-dimensional example